first way for deallocating objects that we'll look at is called reference counting. And reference counting overall is a way that we can keep track of how many times an object is referenced, and so we can keep track if there's any other users other than the one that has just stopped using a record. And the way reference counting work, as the name suggests, is that we start by attaching a count to every object. When you create an object, initially it has a count 0. Whenever you create an object, though, you're immediately installing a pointer to that object somewhere, right, in a register and in another object. When you do that, then you increment the count on the referenced object. So you allocate a numv, say, and you put the reference to the numv in the v register. Then at that point you increment the count on the numv object. Whenever you do that, there was something already in the register, some other value that was being referenced by the register before. You decrement the count on the object that is no longer referenced by the register or that place in another object. And when a count is decremented all the way to 0, that means that the object whose count was just decremented, it can be freed immediately. At the same time, any other object that one references, its counts can be decremented, and so on, which may cause more counts to reach 0 and more objects to be freed. Let's look at this in picture form. In this picture, the blue area is the space of all allocated objects, and each of these green boxes in the blue area, that is an allocated object. The green boxes at the top represent registers, like the continuation register or the value register or the environment register. These numbers on each green box in the allocated object are the reference count. And of course, they're all 1 or more, because if it was 0, the object would go away. At this point then, we have registers referencing some objects, and you can check that every box has a number that indicates how many arrows are coming in. If we change this object so that instead of referring here, it refers to this other object, then we will have to decrement this object's count, because we're no longer referring to it from this point, and increment this object's count, which is why this one went up to 3. At the point where this one becomes 0, then that means we can free it. And as we free it, we also decrement the count on this object, because this old object that went away is no longer referring to it. And then we get back to a steady state, where again every box has a reference count that corresponds to the number of arrows coming in. That was a case of changing a record somehow to point to another record, right? Changing an object and its reference. More often what our interpreter does is it has registers that it changes the references. So for example, if we stop referring to this object here from this register, then that count will go to 0, and therefore it can go away. And when that object goes away, this one down here, its count also goes to 0, which means it can go away. And at this point we're back to a steady state. If we put this into code form, then when we interp lambc, for example, we're going to replace the value register. So the first thing we do is decrement the reference count on the current value. And then we're going to assign into the value register the result of a new allocation of a closure. We assume that when we allocate the closure, that it increments the reference count on the environment, because the closure is a new reference to the environment. And then, after that closure is installed in the value register, we also increment the reference on the closure object itself, because the value register now refers to it. In continue, in the do_appk case, then similar things happen. First, we will extract the new expression from a closure. There's no reference counting there because we're assuming that expressions are allocated statically. So then we move on to the environment record, where the first thing is we need to decrement the reference count on the current environment. And then we set the new environment to a cons, which produces an extended environment, which again we assume increments the reference count on the value that we're passing from the value register and the environment that we pull out of the closure. And then that environment extension is going into the environment register, so we increment its reference count as well. Finally, we're going to increment the reference count on this continuation that's a rest, decrement the reference counter on the old continuation, and then install the rest of the continuation in the K register. Notice that it's important that we do the reference counting in this order. If we tried to decrement the old value of the K register, install the new K, and then increment, that would be too late, because this is probably the only reference to the rest of the continuation, assuming that we don't have letcc. So it's important to increment the reference count on the new extension of the continuation before we decrement it on the old one, and so on. So a benefit of reference counting is that it's relatively predictable. You know when it's going to happen and things get freed as early as possible. A drawback is you have to be very careful writing your code to write down the ref plus and ref minuses in the right place and in the right order. There's another drawback that happens to reference counting in some settings where you have imperative update of objects. For example, suppose our objects look like this. If we change this object that it points back to this object, now we've created a cycle between these two objects. And at this point there's nothing wrong with that, but when we remove the reference in this register to that object, then we decrement the reference count and we end up with 1. And now we have two objects that are not referenced by any other object and not referenced by the register. So we're not using them at all, but it didn't get freed either because the reference counts are all above 0 because there is this cycle. It creates a little island here. So the bottom line is that reference counting does not work with cycles. That's not a problem in our current interpreter because we don't have any imperative features. You can't change an object to refer back to another object, and in general you can't create this kind of cycle. But if we were to add an imperative feature to our language, then we would have a problem with reference counting.